This is Colin Selleck of Binghamton University. This video lecture is for the course ME273 Statics, and we use the textbook Statics by R.C. Hibbeler. Today I'm going to be talking about chapter 4.6, Moment of a Couple. So after today, you will be able to define a couple and determine the moment of a couple. First, we'll look at some applications. We'll look at the moment of a couple, we'll define it, and then we'll do some problem solving. So here we see a wheel being turned by a couple, and the force is 30 newtons here and 30 newtons here. And that's equivalent to this couple here, which is a greater force, 40 pounds, but it's closer together. So the closer together it is, the greater the force that you need to make the couples equivalent. So when you grip a steering wheel with both hands and turn, a couple moment is applied to the wheel. Now remember, older vehicles, if you see videos of them, they have huge steering wheels. That's before the days of power steering, so they needed a large moment arm. So that's why the steering wheels were so large back then. Now a couple is defined as two parallel forces, as you see here, that have the same magnitude and are separated by a perpendicular distance d. Since the resultant force is zero, right, if you sum forces in this direction, the x direction, you get F minus F, and it's zero. So since the resultant force is zero, the only effect of a couple is to produce an actual rotation, or if no movement is possible, a tendency to rotate. For example, imagine you're driving a car with both hands on the steering wheel and you're making a turn. One hand will push up on the wheel while the other hand pulls down, which causes the steering wheel to rotate. The moment produced by a couple is called a couple moment. We can determine its value by finding the sum of the moments of both couple forces about any arbitrary point. For example, position vectors RA and RB are directed from this point O to these points A and B, lying along the line of action of minus F and positive F. So the couple moment produced by these is therefore M is equal to RB cross F plus RA cross minus F. Well, that equals RB minus RA cross with F. However, you can be seen that RA plus R, right, is equal to RB. So RB minus RA is equal to R. This R right here. So we can just substitute that in here. It's R cross F. Now this result indicates that a couple moment is a free vector. That is, it can act at any point since the moment depends only upon the position vector R directed between the forces and not the position vectors RA and RB that we saw in the previous slide. This concept is unlike the moment of a force, which requires a definite point or axis about which the moments are determined. Now, in the scalar formulation, the moment of a couple, as you see here, is equal to the force times the perpendicular distance between the two forces. And this is a scalar, right? Has no direction. Now the direction and the sense of the couple moment are determined by the right hand rule, as you see here, where the thumb indicates this direction when the fingers are curled with a sense of rotation. So these two forces here would tend to rotate this way. That's what you see here. Now in all cases, in this 2D formulation, the moment acts perpendicular to the plane containing the two forces. Now, since couple moments are vectors, their resultant can be determined through vector algebra. So as you see here, we have these two couple moments, M1 and M2. Well, the resultant moment is just the sum of those two vectors. And if more than two couple moments act on a body, we can generalize the concept and say that the moment is equal to the summation of all the R cross F's. Sit down. Now, equivalent couples. If two couples produce the same magnitude and direction, these two couples are equivalent. For example, as we saw earlier, these two couples are equivalent because 0.4 times 30 is equal to 0.3 times 40. Note that the larger forces are required in the second case to create the turning effect because the hands are placed closer together. Also, if the wheel were connected to the shaft at a point other than its center, then the wheel would still turn when each couple is applied, since the 12 Newton meter couple is a free vector. So let's do some examples. Here we see two couples acting on the beam with the geometry shown. Find the magnitude of F such that the resultant couple moment is 1.5 kilonewtons clockwise. So since it's clockwise, that resultant couple is going to be equal to minus 1.5 kilonewton meters. So first we'll add the two couples together to find the resultant couple, and then we'll equate that net moment to the desired couple moment, 1.5 kilonewton meters clockwise. So let's calculate the moments. Let's do the F vector first. And its moment couple is going to be, 0.9 times F, and it tends to want to rotate clockwise, so that's negative. So the resultant moment is minus F times 0.9 meters. Now this 2 kilonewton forces, these 2 kilonewton forces define another couple, and it tends to rotate counterclockwise, so it's positive and its perpendicular distance is 0.3, so this would be plus 0.3 times 2. When you solve, now the resultant moment, as I said earlier, we want to be minus 1.5 kilonewtons. So that equals to minus 0.9 F plus 0.6. So the answer is F is 2.33 kilonewtons. Now let's do the vector approach. Here we have this 450 kilonewton couple defined by FA and FB. Find the couple moment in Cartesian vector notation. So our plan is to use the vector formulation of the moment equation here to find the couple moment. And in this case, R, we can do this one of two ways. We can set R equal to the vector between going from A to B, and in that case the force will be F sub B. Or we could define R is equal to RBA. That means I'm on B here and I want to get to A. In that case we would use F is equal to minus F sub A. And then we'll just calculate the cross product to find the moment. So R of A with respect to B, I'm on A, I want to get to B. Well, all that is, it's 0.4 meters in the I direction. So R A with respect to B is 0.4 I meters. Now F sub B is this one here, and we need to break it into its Cartesian components. Well, in the X direction, there is no component because this FB force is entirely in the YZ plane. So that's just 0I. Now in the Y direction, it's going to be positive, and this is a 3, 4, 5 triangle, and f sub b is 450. So it'll be plus 450 times 4/5 in the j direction. In the z direction, it's pointing down the negative direction, so that means it's minus 450 times 3/5 in the k direction. And when you do that algebra, it comes out to be 360j minus 270k. So now we've got our r vector and we've got our force vector. So we can just say, set up our matrix as we've done earlier in this chapter. So the moment is ijk across the top row. Second row is the vectors, 0.4 in the I, 0, 0 on the jk. And the force vector is 0, 360, minus 270. So when you use the determinant method to evaluate this, you come up with so 0 times minus 270 minus 0 times 360, and that's in the I direction. The next term is negative. Remember, the j one's always negative, so minus, and that would be 0.4 times minus 270 minus 0 times 0, and that's in the j direction. In the k direction, it would be plus 0.4 times 360 minus 0 times 0, and that's in the k. And when you do all that, it comes out that the moment is equal to 108j plus 144k Newton meters. Let's do another example. Here we have two couples. They act on the beam with this geometry shown, and D is 4 feet. Find the resultant couple. So the way we're going to do this one is going to resolve the forces into their x and y directions so they can be treated as couples. And then we'll add these two couples to find the resultant couple. I mean, otherwise, if you didn't do it that way, you'd have to find, the perpendicular distance here. And you could probably do that from the geometry, but it's easier to do it by breaking it up into x, y. Okay, let's do the 50-pound force first. And remember, we're going to break it into its components. So the upper left one, let's do that one. So it has a component here of 50 times the sine of 30, because we're 30 degrees from the y-axis, so sine of 30. And that is to the right, like I drew. So that's equal to 25 pounds. And the vertical component is equal to 50 times cosine of 30, which is 43.3. And it's pointing upwards. So this goes up, this goes to the right. Now, to do both of those forces apply, do they both contribute to the couple, to the moment couple? Well, no, because the x component of the force in both forces lie along the same line, right? One of them points to the left, one points to the right, but they're on the same line. So the x component does not produce or does not contribute to the moment. Only the y component does. I hope you can see that. And of course, the moment here is equal to just 43.3 times 3 feet. And that would be tending to want to go clockwise, so it's negative. So that equals minus 129.9 foot-pounds. So let's do the other force, this 80-pound force. We're going to do a similar thing. let's resolve the lower force into its components. So in the x direction, it's going to be 80 times 4/5. And that's 64 pounds. And it acts to the right. And the y component of that force is equal to 80 times 3/5, which is 48 pounds. And it's acting up. Similar to what we did before, this time the y components of both these forces, they lie along the same line, so they don't contribute to the couple moment. Only the x component of the force does. And it's separated by a distance of 4 feet. So the moment here is equal to the 64 times 4, which is 256 foot-pounds. And it is, which way is it turning? Tends to want to go counterclockwise, so it's positive. So the total moment is just equal to moment 1 plus moment 2, which is minus 129.9 plus 256. That equals 126 foot-pounds. It's positive, so it's counterclockwise. Now let's do another one. This time we're going to use the vector formulation. So we're given that F is 80K, so it's newtons. It's 80K, it's in the Z direction. Minus F is equal to minus 80K. Find the couple moment acting on the pipe assembly using Cartesian vector notation. So we're going to use the vector equation, m is equal to r cross f, to find the couple moment. And the question is, what is r and what is f? So I'm going to go from, that's point A to point B. So my position vector is RAB, and we're going to use the positive value of the force. You could also say RBA and F is equal to minus 80K. Either way. And then we'll calculate the cross product. So first let's find R of A, B. That means I'm on A and I want to get to B. So how far in the x direction? Well, A is 200, right, in the x that way, but B is 300 that way. So you subtract those two and you'll get, I'm going to write it in meters, 0.1 in the I. It's 100 millimeters. In the j direction along the y-axis, well, we're starting out at 300. We go an additional 300 and then an additional 200. So that would be 500 millimeters or 0.5j. It's positive. And that's in meters. And we're going to use this force, which we were told is 80K newtons. So let's set up our matrix to do the cross product. So it would be the I, J, K. Next is the R vector, which is 0.1, 0.5, and 0. And next is the force vector Cartesian components 0, 0, 80. And this is the moment. So let's evaluate this and using the determinant method. So we would get 0.5 times 80 minus 0 times 0. And that's in the I direction. The J, remember, put that minus sign. Minus, it would be 0.1 times 80 minus 0 times 0. And that's in the J direction. Plus, and in the K direction, it just comes out to be 0. It's 0.1 times 0 minus 0.5 times 0 in the K. So the answer comes out to be the moment is equal to 40I minus 8J Newton meters. This concludes the lecture on 4.6 moment of a couple. The next lecture is on 4.7 simplification of a force and couple system, and 4.8 further simplification of a force and couple system. See you in cyberspace.